we started to look at diffusion of innovation, how innovations or adoption of a new technology can spread in a social network. We saw an example, what was called the threshold model of diffusion, when people adopt a new technology or a new product, or maybe even a political opinion, when the majority of their friends already adopted. Next, we're going to consider how this model can arise from rational decision-making. So one way it can arise is when people are coordinating or playing a coordination game with their choice of technologies. So let's start thinking about this with the level of just two friends. Suppose the two friends both are choosing between two competing technologies. Let's call them technology X and technology Y. And we can set this up as a game when these two people, if they choose the same technology, they can benefit maybe from each other's knowledge or from easy coordination between the two technologies. Let's say the benefit is X if they both choose technology capital X, and the benefit is Y if they both choose technology capital Y. We'll allow for X and Y to be different, signaling that maybe one technology X is better than the other technology Y, then X is bigger than Y. And they're going to get benefit 0 if they choose different technologies, signaling that it's harder to coordinate that way. So if I think of this as a 2-by-2 game, this game has two pure strategy Nash equilibria. Either they both choose strategy X or they both choose strategy Y. So far this is pretty simple. What we wanted to consider is the same game played in a much bigger network. So say person A is part of a bigger network, has like 5 friends as in the example, and what we're going to think about next is what is A's rational choice between technology X and technology Y, assuming her friends already have been using different technologies. So say, for example, A has 3 friends that use technology X and 2 friends that use technology Y. So she has 2 choices. If she chooses technology X, she gets a benefit of 3X from 3 of her friends that use X and nothing from the others. If she instead adopts Y, she gets benefit of 2Y from the 2 friends that use technology Y and nothing from the 3 others. So in this case, A should rationally adopt X if 3X is greater than 2Y. This indeed leads to the threshold, majority-based threshold of adoption when X is equal to Y. Let's think about this a bit more generally. So A maybe has D neighbors, and let's say a p fraction of their neighbors adopted technology X, and 1 minus p fraction is adopting technology Y. So similarly, A has a choice between adopting X and getting benefit from the p fraction of the friends that use X, which will be D times P times X, D times P friends, each using technology X, or D times 1 minus P times Y for D times 1 minus P neighbors that all using technology Y. And A should rationally adopt X if D times P times X is greater than or equal to D times 1 minus P times Y. Actually, if the two terms are equal, then person A is neutral between the two technologies. To make our model simple and deterministic, let's assume that A will already adopt the technology when she's neutral between the two. So this is our model of adoption. It's nice to notice that the inequality we have actually has D on both sides, which we can cancel and simplify and say that A should adopt technology X if P, the fraction of her friends using technology X, is at least Y divided by X plus Y. So we're going to call this Y divided by X plus Y Q. That's the critical fraction of her friends. And A will adopt technology X if the fraction P is greater than or equal to Q. When X equals Y, then this fraction is exactly a half, 1/2 X over X plus Y is a half. When X is a better technology, then this fraction is less than a half, and if X is the worst technology, this fraction is greater than a half. So far we've seen a coordination game where each person may coordinate with their friends, benefiting from the friends that use the same technology. And this led to a threshold-based innovation pattern that we have seen earlier. each node adopts in the network if a critical Q fraction of their friends already adopted earlier. This kind of innovation pattern allows innovation to get started in a small part of the network and then spread out. An interesting question we're going to ask next is how far such innovation spreads. Some innovation spreads throughout the whole network, and sometimes it gets stuck after spreading to a large but not overwhelming fraction of the network. What we're going to look at is how this decision or this level of adoption depends on the network structure.